So hi, I'm Ryan. I finished my honours year this year, so this is why I'm here, not flying away to an exotic destination.
We'll pass the mic down that way then. Hi everyone, my name's Felix. I'm MD1 at UMelb, and I'm excited to get into clinical placements next year.
I'm Alex. I just graduated this year, I guess, so excited to get started working next year.
Hi, I'm Shauna. I also just graduated from Monash.
And I'm Lucy. I'm also MD1 at UMelb.
Right. We did not have a team name because we didn't actually think that this was a requirement. So let's start our talk. All right. So welcome to our talk. This is what we've been doing for the past 2 weeks while staring at our laptops and ruining our eyesight. So medical LLMs, modern LLMs are really large and really complex black box models, and they're run by a lot of numbers and matrices and matrix multiplications that we can never really kind of get a grasp of. And so how do we actually try to unravel this puzzle? And that's the core of mechanistic interpretability, which is an emerging field which tries to understand our models by essentially trying to reverse engineer them. So if we can understand our models more, we can extract meaning from them, trust them more, or even steer them in directions to help them be more accurate, or maybe even be more safer to humans. But the issue that we run into is called polysemanticity, which is a natural process where neurons in a large language model are activated or represent multiple unrelated features all at once. And that poses a problem because how do we actually gain a more fine-tuned or a more granular view and control of our model to kind of look into it in a more understandable fashion? So that's where we use this tool called a sparse autoencoder. To kind of unravel these kind of very complex neurons. By forcing these kind of polysemantic neurons through a sparse dictionary layer, we can actually force them to be monosemantic, which means basically they have one neuron representing one feature. And the power of this tool here really is where you can actually identify these neurons which represent these features, label them, and actually tweak them to push our model into a more useful direction for us.
Awesome. So I'll talk a bit more about sparse autoencoders, or SAEs. So in the context of a project, we've broken this down into feature exploration, feature steering, and they'll also mention our limits and next steps. Feature exploration, the main idea here is to identify and physically point to, oh cool, this neuron over here is the one relevant, and this is the one that's being activated the most. We can then upregulate them and see how that modifies the outputs. And our hypothesis is, after upregulating certain medical neurons, we should perform significantly better than a baseline llama model. To talk more about the feature exploration method, what we start off with is going to be a series of case reports, and we're going to be focusing on particular specialities. In this example, we've got a neurology case report from BMJ. We feed that into the sparse autoencoder, and we can see which neurons are lighting up the most and corresponding the most to that particular case report. And then we're able to identify the top activated neurons, for example, this list of 8 over here. We were able to do this by visualizing them on a graph, and we can see that at some point, there's going to be an output point or a point of diminishing returns, where up until a certain number of neurons, that's where we're going to get the most amount of activation given the least amount of neurons.
So feature steering. A famous example you might have once encountered is called the Golden Gate Bridge example. If you normally ask AI, what's your physical form? It would respond, I don't actually have one, I'm a software, I'm AI. And rightly so. However, if you find the neurons for Golden Gate Bridge and upregulate them by 10 times, you find that the AI suddenly discovers themselves as the Golden Gate Bridge. So we tried to bring this forward in our attempt to create a medically aligned model. We upregulated the top 8 neurons by 50 times, and then we tested them against medical exam questions, 200 of them to be specific, just to see how well they would respond. So here you can place a bet on which specialty you think is going to work. We have 200 questions up top, and we can see how many of them they answer correctly. So here at the moment we have unsteered at the top, the neurons coming in close approaching, and that's the result. So we can see that the unsteered model answered 88 questions out of 200 correctly, and the rest of the specialties perform significantly worse. And why that's the case, we will show in our next slide.
So the main thing is that it shows that SAEs can extract some meaning from medical texts. However, there were quite a few limitations which explains the performance. So the first one was the SAE model itself. Because we were limited by time, we had to use a pre-trained model, which was pre-trained on Reddit. And Reddit doesn't have a lot of medical knowledge, which would explain why it's unable to extract very detailed medical information. The second problem is that the SAE model is actually quite small. It only has about 65,000 latent dimensions. And the problem with a small SAE is that it doesn't have enough capacity to capture the fine details and the information you want. So ideally, we would want to pre-train the SAE with medical knowledge instead of Reddit knowledge. The second one was feature exploration. So we only inputted for each specialty 6 BMJ cases, and this is very small, which would explain why I only had limited knowledge. The second one is that we only had one structure, so which was a BMJ clinical case. And because of this, we were activating a lot of syntax-related neurons. So in future, we want to provide more variety medical text so that we don't have these syntax-related neurons interfering and confounding our interpretation of the models. And the second one is that we want to do more experimentations. For example, we only use seed number 42, and ideally want to see what would happen, would the performance be better if we experimented and changed this number.
We also had some limitations when it came to feature steering because we ironically had to take a really blunt approach due to time limitations. So firstly, this meant that we just picked the top 8 features, and for some specialties this worked quite well, but if we look at all of them, you can see that for others, even beyond the top 8, some actually have reasonably high activation. Even within the top 8, we can see that there's a lot of variance in activation levels that we didn't replicate when we were doing feature steering. For simplicity, we just upregulated all of these neurons the same amount when we were feature steering. This was mostly because we couldn't really take into account what these neurons actually represented. And we just kind of guessed that the top 8 were the most relevant and kind of had to operate under that assumption. And sometimes that was correct, like this is the second most strongly activated gastroenterology neuron, but sometimes it is more to do with the type of text that we fed it instead of the content in it. We did try to identify these neurons, but ran into more issues there. Firstly, namely that not all of them actually had labels in the code that we were given. So of the top 8 gastroenterology neurons, we only had definitions for the top 2. This is, for a bit of background, the definitions of these features come from inputting a corpus of text and then finding the top 50 sentences that activate each neuron and then kind of summing up their meaning and averaging them out to make this feature ID dictionary that tells you what each neuron kind of represents. So this means that not every single feature will have a label because some of them may not have had 50 sentences activating them in the first place. So we tried to do this ourselves. We unfortunately couldn't use all of Reddit because that would take a lot of time. And so we thought it would be much more, instead we just used the text that we used in feature exploration, but that didn't end up working very well. So for a reminder, these are the labels that came from using all of Reddit to do the feature labeling. But when we used the case reports that we actually fed it, the feature IDs turned out to be slightly less interpretable. And this is because the language that is used to describe what the features are has to come from the language of the input corpus. So in future, even though we want to train more medically aligned SAEs with probably medical text, this step we realized would need a varied dictionary to actually give the model the language it needs to tell us what the features are. So in summary, we did a proof of concept that SAEs can interpret medical text and highlight medical neurons, but showed that the blunt force, unlabeled approach means that models actually perform worse on average. And next step would be to retrain a medically relevant SAE with thorough feature identification for more purposeful feature steering.